Hello, this is at THS Mr. Jones, and we're going to talk about chapter 5.5 today, which is exponential and logarithmic models. Now, that's just a real fancy word for saying word problems. Okay, so we're dealing with word problems today, and there's 5 different models that we're going to look at, starting with exponential growth. And we've got exponential growth and decay. We're going to kind of do them both at the same time. So we have their graph, and exponential growth looks like that. And exponential decay is just reflected over the y-axis there. They both have equations. So n of t equals n naught e to the rt. And then this one, since they're just flipped over the y-axis, they look very similar to the minus RT on that. And we have, I'm going to write a list here of some places we see this in real life. So we can say world population. Bacteria growth, HIV, AIDS, virus, and there are many others. Okay, especially this one. This is any communicable disease, so like flu or Ebola or anything like that. With decay, we have half-life. We have carbon dating. And we have depreciation. Okay, carbon dating is just telling how old something is based on the carbon molecules left in them. And depreciation is like value. So when you drive or own a car, how much money it is losing over time. The next two, we have the Gaussian distribution, and we have the logistic growth. So Gaussian distribution looks like this. Okay, and logistic growth looks like this. Again, these have formulas. And then the logistic growth. Now, the nice thing about these problems is we can always look up these basic models here. And I'm going to give these equations to you, so you'll never have to know these two equations. So some places that we see Gaussian distribution would be the bell curve, or grades, any height, weight, and I'll put BMI on there, IQ or life expectancy, and laser intensity. Okay, those are just a few. Education uses the Gaussian distribution quite a bit with grading and fitting kids onto a normal scale. Like here would be your A's, your B's, your C's, your D's, and your F's. Okay, so this is how you should really want your grades scattered out. So a majority of your kids, or your average of your kids, are going to get C's. That's where you want. Anything better than that obviously is good, but anything less than that would not be good. But this is ideal right here. It's skewed one way or the other if it's different. So for logistic growth, we have conservation biology. We have the learning curve. We have closed virus. And we have carrying capacity of like a bridge or of a crane or of any other construction equipment. Okay, so there's those two. And then we have logarithmic. Okay, logarithmic, its graph, which we've dealt with a couple times before, will look like that. And its equation is fairly simple compared to the others. Is there. And we have population of a species. We have anesthesia wear off. And credit card payoff. Okay, so since we have a lot of formulas here, we're going to have a lot of variables. So I'm going to go over some common variables that you might see. So we'll say, first off, R is rate, T is time, and then we have P naught or N naught, which is population at time t or number at time 0. Or your starting population. We have M naught, which is the initial measurement or measurement at time 0. We can say those all different ways. P is principal. LE. We have A, which is amount. We have sigma, which is a lowercase Greek letter for standard deviation. We have sigma squared, which is your variance, which are measurements of how spread out data is. You have mu, which is mean. N, which is number of compounds. We'll have I, which is often used for R over N, so your rate divided by your number of compounds. We have T, which is temperature at a given time. We have TS, which is your surrounding temperature. And we have T naught, which is your initial or start temperature. And of course, there are many, many more common variables that may show up, but this is just a list that I thought would be rather helpful. So we're actually going to stop here, okay? And you can, let me find the questions. So here are your 2 questions. So we need to bring our book to class because these are word problems. And yeah, they're all in your books. So bring your book to class. And then number 2, what formula would I use for population growth? Here are some suggested problems. There's not very many of them. 51's your challenge problem. I try to pick not very many, but I try to spread out among different varieties. So like there's a couple there's a finance, there's a school grade one, there's one where you find out like what time somebody died. There's a population one, all sorts of ones. So go ahead, stop here, and take a look at those suggested problems. Okay, if you're sticking with us, we will go over some examples. All right, let's get some paper here. All right, so the first example we'll look at is, well, let me just read it to you here word for word. Okay, the world population is the total number of humans on Earth at any given time. In 2000, the world population was 6.1 billion, and in 2005, the world population was 6.5 billion. Find the relative growth rate and determine what year the population will reach 9 billion. Okay, so if we make some notes here. So in 2000, we had 6.1 billion. And in 2005, there were 6.5 billion. And I want to know one, what's the growth rate? And I want to know two, what year will it be when I have 9 billion? Okay, in order to find our growth rate, we'll use this formula NT equals N naught E to the RT. Okay, I know these dates and these populations, so I'm going to use those for right now. So I know that the N population was 6.5, and I started with 6.1. I have E to the R, I don't know, but I know that it took 5 years to do that. Okay, so now all I have to do is solve for R. So we'll divide by 6.1. Okay, and we'll have 6.5 over 6.1 E to the 5R. Okay, now I need to get rid of E. So all I'm going to do is take the ln of both sides. Ln of both sides. So that cancels with my E. So I have ln 6.5 over 6.1 equals 5R, and divide by 5. Now the cool thing is I can put this whole thing into the calculator. So we can say ln 6.5 divided by 6.1 divided by 5. And you'll get your rate. I want to change this to a percent, 1.27%. Okay, or if I can't, we'll do 6.5 divided by 6.1, enter. I want to keep using this long decimal. I don't want to round until the very, very end. So now when I take the ln, the log, I'm going to take ln and I'm going to hit second, and then this negative button down here where it says ANS. So that shows up the logarithm of the previous answer. And we'll hit enter, and then we'll divide that by 5, and we get the same answer. So now that I have my rate, I want to know what year am I going to have 9 billion, okay? So I know my ending. My ending is 9 billion. I know my start is 6.1. E, I know the rate now, which is 0.0127, but I don't know the time. So it's the exact same process as it was over here, just different numbers. So divide by 6.1. So I have 9 over 6.1 e to the 0.0127t. And in order to get rid of e, we're going to take the ln, and then we're going to divide by 0.0127. Okay, so if I put that in the calculator over here, we'll have ln of 9 over 6.1 divided by 0.0127. And t is 30.6. Okay, so my start time was 2000, so 30.6 later is 2030, and we're actually 0.6 of the way through. So 12 months, and 60% of that is in July. Okay, so we're going to be sometime in July where we hit 9 billion people. Yeah. So that was a world population one. Okay, I kind of like radioactive ones, so we'll look at this problem. So the radioactive isotope of potassium K42, which is vital to the diagnosis of brain tumors, has a half-life of 12.36 hours. Determine the exponential decay model that represents potassium 42. If 500 milligrams of potassium 42 are taken, how many milligrams will remain after 48 hours? And how long will it take for the original 500 milligram sample to decay to a mass of 5 milligrams? Okay, so we'll just do it here. We've got potassium. No, let's get a different color here. We got potassium 42. Okay, and its half-life is 12.36 hours. Okay, so we had a couple questions. The first one was find a model that represents this. Okay, I gave you an equation for this. That look like that. But the book also gives a little bit different equation, and it looks like this. Okay, and it says the rate equals, which this is just exponential growth, or exponential decay because of that negative, that the rate is ln2 over h, which is hours. Okay, so we can kind of compare both of these, and we'll look at which one's more accurate or which one gives you a better result. Okay, so the first thing I need to do is find my rate. I need to plug in my 12.36 hours in here. So this one will be P equals P naught 1/2 T over D, which is your decay rate. So 12.36. So that one's done. Here we've got the ln2 over H, which is ln2 over 12.36. And when I put that into the calculator and sub it back in here for R, we'll have M equals M naught E to the negative 0.0561 T. Okay, so my models are two different models, but we should get out fairly similar results. Okay, and the first question was, if 500 milligrams, how much in 48 hours? So we'll start with 500 milligrams, and I want to know in 48 hours. Okay, so when I plug that in, let's kind of split this in half so I can do each one. When I plug it into this one, my ending amount I don't know. My start amount is 500. I have e to the minus 0.0561 times 48 hours. Okay, so all I got to do is put that into the calculator. And when I put that into the calculator, I have 500 e to the negative 0.0561 times 48. We get 33.85. So 33.85 milligrams. Okay, when I do this other one over here, we'll have P equals 500 half 48 over 12.36. Okay, so on my calculator here, we'll do 500 1/2 raised to the 48 over 12.36. And we get 33.88 milligrams. Okay, so a little bit different answer for those two. All right, and the third part said, how long will it take for the 500 milligrams to go to 5 milligrams? So in this case, we know start and stop, and I want to know the time. So if I want to go to 5 milligrams, but I start at 500, I'm looking for T. Okay, so we'll divide by 500. We'll get 1 over 100 equals e to the minus 0.0561 t. All right, so then to get rid of the e, we'll take the ln of that whole thing and divide by negative 0.0561. Divide by negative 0.0561. So I have ln of 1 over 100 divided by negative 0.0561. And I get 82.1. So 82.1 hours. Okay, because that was time. And if I do the other one here, we'll end at 5 again. We'll start with 500. 1/2 t over 12.36. So again, divide by 500. Okay, so I'll get 1 over 100 equals 1/2 to the t over 12.36. And because I want 1/2 to go away, that's my base, I'll have log of base 1/2. So log base 1/2. So these two cancel. And I have t over 12.36. So we'll multiply by 12.36. So those cancel. So 12.36. So in our calculator here, we'll put 12.36. And I need to use a change of base formula here. So I'll put parentheses. I want log of 1 over 100 divided by log of 1/2. And I get 82.1 hours. Okay, so in this case, I got the exact same answer. Okay, so because it's a different model, it'll vary just a little bit, but it is not a ton of variance on that. All right, so let's look at one more here. So James owes $15,000 on his credit card. Bad job, James. The annual interest is 13% compounded monthly. A, find the time it will take to pay off his credit card if he makes minimum payments of $200 per month. B, find the time it will take to pay off his credit card if he makes payments of $400 a month. Okay, so James owes $15,000 at 13% monthly. Okay, A, $200 payment, and B, $400 payment. So we're going to double it. Okay, well, the book actually gave you a formula for this. And the formula is T equals negative ln 1 minus PR divided by NR over N ln 1 plus R over N. And it says that R is your payment. Okay, so super easy. I just got to plug in my numbers and put it into the calculator. So for 200, we're going to say the time it takes is equal to negative ln 1 minus 15,000 times 0.13 over 12, which is my number of compounds, times 200 over 12 ln 1 plus 0.13 over 12. Okay? Big long thing. We'll put it into the calculator here, and let's see what we get. Okay, so you have negative. Remember, lots and lots of parentheses will be helpful. So we'll put the whole top in parentheses. So ln of 1 minus 15,000 times 0.13 divided by 12 times 200. Okay, so end the ln, end the top, divided by, put the bottom in parentheses, 12 ln of 1 plus parentheses 0.13 over 12, parentheses, parentheses, parentheses. And we will get that it will take him paying $200. It will take him, looks like 13 years. Okay. So now we're going to run the same formula, except now instead of 200, we're going to put in 400. So ln 1 minus 15,000, 0.13, 12, 400, 12 ln 1 plus 0.13 over 12. Okay, but it's nice in the calculator here, we can just hit second enter and it'll retype all that, and we'll just go up here and put a 2. Okay, so now instead of 13 years, it's only going to take him 4 years. So you'd think it would only half it, but half would be 6.5, but it actually splits it way better than just half. So I'm paying double, not necessarily going to cut down half the time. Okay, so we'll stop here. Again, there's a ton more examples I can do, but it's just hard to get them all in. Again, here's your suggested problems. Make sure you do them, ask questions, and be ready for your quiz. Make sure you subscribe to the channel, you like and comment on this video, and let me know what you think. As always, this is at THS Mr. Jones signing off. Thanks for watching.